1, 2, 3, 2, 1, ready. So, to the public at home, we are starting this lecture on entropy and thermodynamic potentials. So, I'm going to keep all the applications of thermodynamics and even calculations of entropy for some examples, for some typical systems like the ideal gas or some other systems. We are going to do them tomorrow, okay? And then we are going to enter the field of statistical mechanics either on Friday or next week. We'll see. It depends on how long I want to dwell on thermodynamics. But today we are going to go through all the definitions of thermodynamic potentials and why they're useful, etc., etc. Now, we are going to use all these words like enthalpy, Gibbs potential, Helmholtz potential, and all these kind of things that I'm sure that when you have seen them the first time, you all hated them. At least that was my case, because I did not really understand why they were useful and why people were trying to make my life miserable with Maxwell relations. It turns out that they are very useful, but in order to understand why they're useful, you have to understand why they were introduced. Okay? So, as I told you last time, thermodynamic potentials were introduced because you want to find what is the equilibrium state that is realized in a system under certain constraints, okay? Of given volume or given temperature or given pressure or given pressure and volume or given temperature and volume and so on and so far. And it turns out that the thermodynamic potentials give you the answer to these kind of questions. So last time we have been introducing using the fact that for reversible transformations, dq over t is an exact differential. We have been using this to introduce a state function, and we called it entropy. And so if you want to compute the entropy at the point B, this is minus the entropy of the point A. It's just enough to choose a path that connects A and B and to integrate over this path. It doesn't matter which one it is, it's as long as you choose a reversible transformation, dq over t. Now, why the entropy is an interesting quantity? Because suppose that we consider a cycle, right, like this one. So a thermal engine, so which operates between temperature T2, temperature T1, sucks some heat Q2, gives some heat Q1, and then does some work. So let us consider the change in entropy in this system. So for this system, I consider the total system. This is not a thermally isolated system. It's a system that is made up of an engine, which is coupled to two reservoirs. So that is my universe. So I want to consider the change in entropy of the entire universe, so which is very simple in this particular case. So delta total is equal to the delta of the engine plus the delta S of the reservoir T2 plus delta S of the reservoir T1. Okay? Great. So now, what is delta S of the system? What is it? Over one cycle.
If it's reversible?
No. This is the wrong way of posing the question. What is delta S of the system? Zero. Doesn't matter whether it's reversible or not reversible, right? Because as long as it is a cycle, the final state and initial state in the parameter space are the same. right? And therefore, if you look at the formula, no matter, you use the Clausius or whatever theorem, etc., integral dq over t over a cycle, over a reversible cycle is equal to 0, and therefore the entropy difference is going to be equal to 0. Okay? So, delta S is going to be equal to 0. Now, what about delta S of the reservoir at temperature T1? Now, here you have to be careful about conventions, right? So, we always have had the conventions that the heat is positive when is given, right? When the system gives it to the external whatever. So in this particular case, however, the system is the heat is positive when it's absorbed by the system. Right? Sorry, I messed it up. In the first principle of thermodynamics, when we wrote delta E equal to Q minus W, so the fact that Q has a plus sign means that the heat is positive when it's given to you, right? When the system absorbs it. But in this case, the system is the reservoir itself that gives the heat to the engine. And therefore, delta Q is going to be T2 is going to be equal to minus Q2 over T2, right? Where Q2 is a positive number. Now, the same thing is going to happen for the reservoir at T1. But the difference in this case is that the reservoir at T1 gets heat from the engine, and therefore Q1 is going to be negative for the reservoir at temperature T1, right? Now, what is the total change in entropy? Delta S total then. Delta S total is minus, what?
Why do both have minus sign?
Because, it's the other way around. If it would be the system, we would have a plus sign. But here we are computing the change in entropy in the reservoir. And therefore, when the system absorbs energy, the reservoir loses energy. And therefore, it gets a minus sign. You see?
But the system absorbs from one side and gives to the other side.
Yeah, exactly.
So one should be negative and the other one should be positive.
Yeah, that's exactly what is happening. I mean, I'm counting, what you just said comes from the fact that Q2 is positive, and therefore this delta S is positive, and Q1 is negative. Sorry, this is negative, and Q1 is negative, and this is positive. Okay? So, therefore, if I put in these two things together, plus Q1, T1, and this is what? This is, according to what we wrote down last week, this is going to be positive because Q2 over T2 plus Q1 over T1 was negative, right? Because of Carnot theorem, essentially. So therefore, this has a minus sign, has to be positive. So what did we just prove? Something very simple, that when you use your cell phone, you're increasing the entropy of the universe. When you're, steering something or using some engine, no matter what, you keep increasing the entropy of the universe, right? The entropy is something that, if you consider the entire system, your engine plus the reservoir, keeps increasing and increasing and increasing. So that's why eventually people say, well, eventually, the entropy of the universe will reach the maximum, and that will be called eternal death. But it doesn't concern us, because in any case, it's going to happen in a few years. Okay? So we don't care. It's okay. Life is beautiful anyway. The world is going to end, fine. That is going to end in a few years. Okay, so now that we know that the world is going to end, what kind of other consequences can we take from the definition of entropy? Well, another consequence is comes directly from is the so-called, let me write it, ellipse Duhem relational relations. So what are these Gibbs Duhem relations that have this nasty name? It's something extremely simple. If we use the first principle of thermodynamics, dE is equal to dQ minus dW, right? So, therefore, what we have is that E, if we use now, if we are on an infinitesimal reversible transformation, okay, then this is going to be equal to TdS minus dW. This is because of the definition of entropy, right? And now we use the definition of W, and this is going to be TdS plus sum over I yi dxi plus sum over alpha mu alpha dn alpha. And then you have the chemical part of the work, which is controlled by chemical potentials. And then you have all the generalized forces, which, for example, for the case of, let's use a color that we never used, something peculiar, this. For the case of, let's say, in which xi is volume, then that means that yi is equal to minus the pressure, okay? And that's it. I have tons of colors, so I can use whatever I want. All right. So, and in particular, this relation implies something very simple, that if I wanted the temperature, this is going to be equal to the derivative of the energy with respect to the entropy whenever I fix all the xi and all the n alpha, right? If I want yi, this is going to be equal to dE dxi fixing temperature and all the n alphas, and at the same time the chemical potential is going to be equal to dE d n alpha at fixed temperature and xi. And now, when I write things in this way, it's obvious that my energy is seen as a function of the entropy, of the generalized forces, and of the number of particles, right? Because the differential is written up in terms of these variables. Now, these variables turn out to be all the possible extensive variables you can dream of in a system, right? Because these are the generalized forces. These guys here are all extensive parameters: volume, magnetization, polarization, whatever, all extensive. Same thing for this one, and same thing for this one. So this is a writing of the energy in terms of extensive quantities. So let me write it like this. Let's use another code. Today we experiment. We make experiments. E is now a function of the entropy of all these parameters xi, which are conjugated to the generalized forces, and all the numbers of particles, which are conjugated to the chemical potentials. Okay? And now, these are all extensive parameters. The energy is intensive, extensive, sometimes in what? Out loud. What is it? The energy is extensive. Good. So the energy is extensive. What does it mean? What does it mean that the energy is extensive? It means that if I take E evaluated on lambda times S, lambda times xi, and lambda times n alpha, okay, so if I increase the volume by a factor lambda, and therefore the entropy increases by a factor lambda, and therefore the number of particles increases by a factor lambda, if I fix the density, of course, then the energy will increase also by a factor lambda because it's extensive, right? So let's now take a derivative with respect to lambda, okay? With respect to, this WRT means with respect to lambda. If you take the derivative with respect to lambda, then you will discover that the energy is equal to S dds plus sum over I xi d dxi plus sum over alpha and alpha d dx alpha dn alpha, right? Correct? And now let's go back. We know that dds is t, ddx is y, ddn is mu. Therefore, what we just discovered is that this is equal to S times t plus sum over I xi yi plus sum over alpha and alpha mu alpha. Correct? It's just a consequence of the fact that the energy is extensive. Now the problem is that we also wrote down before this expression. I'm not going to rewrite it because I'm not on a blackboard, but I'm on a beautiful iPad. So I'm going to use technology, copy, and paste. Good. So we also know that dE is equal to TdS plus blah, blah, blah. This is the first principle of thermodynamics. Now, you see that if I now use this equation, this one, and take a differential, so I will get, when I, for example, take dSt, I will get S dt plus TdS. And same thing for the other terms. Now, all the terms in which I have TdS, so something intensive times something extensive, will be collected and go into this one. And then I will have all the other terms. Okay, let me do it because otherwise I'm afraid that it's just a mess. Take a differential. So you will have dE equal to TdS plus sum over I yi dxi plus sum over alpha mu alpha dn alpha. And then I will have all the other terms in which here I have the entropy and I have the differential of something intensive. Okay? So sum over I xi dyi, sum over alpha and alpha d mu alpha. Okay? But now, the only way to have this to be consistent with this is to have that S dt plus sum over I xi dyi plus sum over alpha and alpha d mu alpha is equal to 0. Okay? That's the only two. So this is the Gibbs-Duhem relation. So what do you use it, what can you use it for? Well, I don't know. If you're given a problem in which, for example, you are filling up a container at a fixed temperature and you want to find how the pressure changes with, with a chemical potential, that will tell you that minus P dV plus mu dN, sorry, yeah, minus V dP plus N d mu is going to be equal to 0 because dt is equal to 0 at fixing temperature, fixed T. And therefore that implies that dP d mu is equal to N over V is equal to the density, right? And so on and so forth. So just something useful if you want to find relations between intensive quantities, okay, not extensive. So you have to keep in mind Gibbs-Duhem intensive, okay? Great. So now it's time to start the super boring list of thermodynamic potentials. Okay? So let's write it. Super boring list of potentials. I'm sorry for the public at home, but maybe we'll put some music in the middle. All right, so the first potential we want to introduce is just internal energy. So we consider a system that is insulated and in a box of volume V, so fix the volume. And fix the volume V. Then, well, internal energy is our beloved object that satisfies our beloved equation TdS minus PdV plus mu dN. Okay? Which implies that, as we all know, T is equal to dE ds at fixed. I will write it only once, okay, and then we understand for the rest of the lecture. Otherwise, I will have to write at fixed blah 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 10,000 times. At fixed the others. Okay, so whenever you will see a vertical line, means at fixed all the other variables. Okay, I don't want to write them all the time, please. So pressure is going to be equal to dE ds, and chemical potential is going to be equal to dE dN. All right? Now you see that essentially whenever you choose a thermodynamic potential, this is the simplest possible, internal energy, you're essentially thinking about using as your variables, as your independent variables, three variables. In this case are the entropy, the volume, and the number of particles. Okay?
This should be a minus dE by dV.
And there should be a minus here.
dE by dV.
And there'll be a volume. You're absolutely right. I got totally lost. Absolutely. Okay. So you're thinking of choosing as independent variables three variables. In this case, the entropy, volume, and number of particles. variables, all the extensive variables as we have seen before. Now, why is it useful to introduce the internal energy? Because according to the first principle of the second principle of thermodynamics, if I am on a generic transformation, not on a reversible one, and a generic transformation is what I get for a generic infinitesimal transformation, and this is smaller or equal for a generic transformation than TdS minus dW. So in other words, TdS minus PdV plus mu dN. Okay? And therefore, this equation tells me that if I fix the entropy, the volume, and the number of particles, okay, any transformation that I'm doing on the system tends to lower its energy. Okay? So dE has to be always smaller or equal to 0 if I fix those three variables. Okay? So, in other words, each process will eventually tend to diminish the energy that will eventually stabilize on its minimum. The minimum of the energy is going to be the equilibrium state, because you cannot get even lower than the minimum. This is something obvious. You all know that the minimum of the energy is, for a system in which you fix, that is essentially thermally isolated, and you fix entropy, volume, and number of particles, the minimum of the energy is the equilibrium state. I think it's an obvious mechanical statement. But it's nice to see that it follows from thermodynamics. Now, another thing that follows from this is that dW, if you rewrite this equation, this one has to be smaller or equal than TdS minus dE. And therefore, again, if fix S, V, and N, then dW is always smaller or equal than minus dE. So this is the maximum work that the system can do on the external environment. Okay? So it's a constraint. This sign comes essentially because of our conventions. Okay? All right. So you have to keep in mind this. Sorry. And you have to keep in mind this. So these are the two relations that characterize a thermodynamic potential. All right. Now, let's consider another important thermodynamic potential. So this is the thermodynamic potential for a completely isolated system in a volume, blah, blah, blah. Let us consider another one that is very important for statistical mechanics. Okay? So this is the thermodynamic potential that describes a system that is in contact with a reservoir at temperature T. Okay? So, this object here is defined as follows. You essentially define it as F, your new thermodynamic potential, as the energy minus T times S. Now, there is some logic behind this. Here, I want to be able to fix the temperature, and the temperature is the conjugated variable of the entropy, right? Now, when I want to switch from a variable entropy to variable temperature, what I do is I put a minus T times S here. Why? Because dF is going to be equal to E minus dE minus d T times S. But this is going to give me minus T ds minus S dt. Now, dE, if you look at, for example, what is written here, contains TdS. That will cancel with this one, and therefore what will remain is S dt minus P dV plus mu dN. Okay? So by subtracting this term, I achieve the fact that I'm changing variables from entropy to temperature. Okay? Great. Now, this little object here has a name, is called Helmholtz free energy. Or just free energy. In most of the cases, you will find it in the literature called free energy, because E is the free energy by default in statistical mechanics. This is going to be for us when we will deal with, you all know that there are three ensembles in statistical mechanics: the microcanonical, the canonical, and the ground canonical. In the microcanonical, you just fix the energy, the volume, the number of particles, etc. And therefore, the only thing, the thing that will make contact between statistics and, you always want to calculate something in terms of probabilities. This is the goal of statistical mechanics, but you want to compute some thermodynamic function in order to use it to do thermodynamics. So what you will do for the microcanonical is compute the entropy. Because the entropy is the thing that connects Newton with thermodynamics in the microcanonical ensemble. In the canonical ensemble, which is an ensemble of a system that is coupled to a reservoir at a fixed temperature, it turns out that the thing that makes this connection is the Helmholtz free energy, okay? Which is indeed defined in order to describe such a system. So that's why this Helmholtz free energy is important, unlike the entropy that I'm going to write down now, but in a few minutes. But since you're not chemists, and hopefully you will not become chemists, eventually you're going to forget in a few lectures, okay? That's what happened to me. We'll see. Maybe some people remember it, and those who do biological physics, but in my case I forgot. All right, so what about relations? Okay, so it's straightforward to compute the entropy in terms of the Helmholtz free energy. You can easily compute the pressure in terms of the Helmholtz free energy. And got the wrong side here. And then you can compute the chemical potential. And finally, you can use dF equal to, on a generic process, dE minus dTs. Okay, so now if I have a generic process, this is going to be smaller or equal than minus S dt minus P dV plus mu dN. Same story as before. I mean, it's just a change of variables. And therefore, this implies that if I fix temperature, volume, and number of particles, then fix temperature, volume, and number of particles, then dF is always decreasing. And that also tells you that, unlike the previous system, the equilibrium state for a system that is in contact with a reservoir at some temperature is the minimum of the free energy. Okay? Keep this in mind, because it will come back when we will do statistical mechanics, and in particular something called mean field theory. Okay? So keep it in mind, it's important. So minima of the free energy for this kind of, in these conditions, realize the equilibrium states. Now what about other potentials? I know, there is another thing that is important. Again, as before, you can discover, if you go through the first principle of thermodynamics, that in these conditions, if you fix temperature, volume, and number of particles, then you will have that the work that you do on the system is always smaller or equal than minus dF. Some of you might have seen this relation written the other way around. It depends on your conventions for work, etc. Right? So this is the work done by the system, and that's why you get this minus sign. All right, so these are the two important relations. Now, finally, we get to assist to this object that is so important for chemists and is so hated by theoretical physicists, which is the enthalpy. So in which case you just fix the pressure. So we have to fix pressure. Let's see if you understood how it works. What do? We want to change variables from volume to pressure.
We'll do minus dPV.
Minus?
Derivative of PV.
Derivative of. So we want.
Plus of PV.
So we want something that we call enthalpy. Okay. So we want a new potential. We'll start with the energy, and now we want to change variables and go from volume to pressure. What do?
Plus P D
Plus P
PV.
P times V. That's it. I mean, no PD. We don't differentiate yet. So plus P times V. Why? Because if we do so, then here, when I take a differential, there's going to be a term of minus PdV. And here I'm going to get plus PDV plus VdP. And VdP is the thing I want, right? So eventually I will have that the differential of my enthalpy is TdS plus VdP plus mu dN. Hope it's correct. Yes. And then, of course, the temperature is equal to dH ds. The volume is equal to dH dP. And the chemical potential is dH dN. All right. Of course, as before, dH is going to be smaller or equal for a generic process than TdS plus VdP plus mu dN. And if I fix number of particles, pressure, and entropy, the variation is going to be smaller or equal to 0, and therefore the enthalpy is going to be the thing that determines, when you minimize it, the equilibrium states of your system under conditions of pressure, volume, and number of particles that you're selecting, and at the same time dW is going to be smaller or equal. If you fix pressure, volume, pressure, entropy, and number of particles, then minus dH. Okay? So now, and I was just thinking what is a condition in which I fix the pressure. But let's not dwell too much on this. Now, another potential.
I have a question.
Yes, absolutely.
The equilibrium state it describes, the equilibrium state it describes, does this give any explanation on how the equilibrium state is? Because the H can be 0 for a maximum and then a minimum, and for a maximum.
No, but here it's always decreasing, right? The H is always smaller than 0. If you fix, so you're always going, if it would be increasing, then you would be going to a maximum. But since it's decreasing, you're going to a minimum. Now, you might have some issues because you might be going, there might be multiple minima, right? And some of them might be local minima, some of them might be global minima for your free energy, for example. This is, for example, what happens when you have a phase transition, in which case if you have a first order phase transition, at the critical point, the system has indeed multiple minima that are competing and phases are coexisting and they try to go one to the other. So this is essentially what is happening. We'll see this. But essentially always decreasing whatever you're computing, right? So be it Helmholtz free energy or enthalpy or whatever. Let's try to go a bit faster now because I see that you're falling asleep. All right, so now we fix temperature and pressure. What do we get? We get Gibbs free energy. So let's see if you understood how to do this. I want to fix temperature and pressure. What do? I take the energy and what do I add and subtract? I want to fix temperature, so minus Ts, and then pressure plus PV. Great. So this is Gibbs. You do the calculations, you will discover that, for example, dGdt is equal to minus S, dGdP dV is equal to, dGdP is equal to minus 2V, and dGdN is equal to mu. Then, of course, if I fix, in this case, temperature, pressure, and number of particles, I will get that dG has to be smaller or equal to 0, right? And then, of course, I will have that my dW is going to be for a process in which I fix these three variables, smaller or equal than minus dG. So this is the same as before. I'm not going to redo the calculations for the 10th time. Now, there is one peculiarity of the Gibbs free energy, which is the fact that, you should consider the fact that before we discovered the Gibbs-Duhem relation, which tells us that the energy is T times S minus P times V plus mu times N, right? But the Gibbs free energy is defined as energy minus T times S plus P times V. Now, if you use the Gibbs-Duhem relation in combination with this definition, this comes out to be equal to mu times N. And that's it. Okay? And nothing else. Now, what about the last one? The last one is called the ground potential. Ground potential. which is, you know, it's a great name to have. It's a potential in which is the one that is connected to the ground canonical ensemble. So it's always ground. And is a system in which you fix the temperature, the volume, and you fix the chemical potential. You don't fix the number of particles. Okay? So we want to fix volume, we want to fix temperature, and we want to fix chemical potential. So we take the energy, so we call the ground potential omega. We take the energy, and what do we do with it? We want to fix temperature. So if we want to fix temperature, we subtract T times S. And we want to fix now chemical potential instead of number of particles. So what do?
Minus
Minus mu1. Great. If you do so, then you get that your d omega comes out to be equal to minus S dt minus p dv minus n d mu. And then you get, oh, so painful. Now, there is one important thing to notice. Well, you get all the standard relations, so you get that your entropy is equal to minus d omega dt, your pressure is equal to minus d omega dv, and your your number of particles is equal to minus d omega dn. All right, now let's put now this thing together with the Gibbs-Duhem relation. Okay, so put Gibbs-Duhem. Use Gibbs-Duhem. Then what we get is that the chemical potential is equal to minus P times P. Okay? Because the energy is equal to Ts, so minus Ts is gone, minus PV remains, and then Q plus mu n, that goes with minus mu n. Okay? Now, this tells you something important that we will see again in statistical mechanics. You know, you read, all of us remember like a poetry, P times E equal to N times R times T, or NKB times T, whatever. So, when you see something like this, the first thing you think about is equation of state. Okay? You see it as an equation of state. I have it. So, and this is indeed the point where the connection between statistical mechanics and thermodynamics comes in the ground canonical ensemble. The ground canonical ensemble is very useful if you want to directly compute the equation of state. Okay? It's a peculiarity. So, essentially, we will see that all the three ensembles are equivalent in the thermodynamic limit. So in practice, you do calculations which, you know, with a microcanonical, canonical, or ground canonical, that depends on you. It's up to you which one you choose. But it turns out that each one of them has you know, is connected to a different aspect of thermodynamics. And therefore, when I want to compute, for example, an equation of state, then I better do the calculation directly with the canonical and ground canonical ensemble, as we will see. When I want to compute the free energy and see what is the minimum state, I use the canonical. And the microcanonical only if I want to suffer. Okay? Because it's typically calculations in the microcanonical ensemble are much more cumbersome. I mean, there are exercises in combinatorics to some extent. All right, so now let us finish.
Can I have a question?
Yeah, sure.
In every potential that we defined right now,
Yes.
it included, can you just go to the previous
No.
page? So, for example, in this grant potential, the temperature which is intensive
Yes.
is coupled with its conjugate
Yeah.
extensive
Which is
quantity entropy and so on, but energy is extensive quantity which is not coupled with anything. So is there any conjugate variable to energy, or for example to the grant potential, or
Oi, oi, oi. Is there any conjugate variable to energy?
intensive, of course.
Mm,
Should be a dimensionless quantity.
Yeah.
yes.
Yeah, if it's dimensionless, it doesn't make sense. Yeah.
No, no, no. Of course, I mean, there is no conjugate. I mean, there is no conjugate variable in that sense in this context. I'm just thinking because there is a formula that I will write down in a second that essentially tells you that the inverse of the temperature is equal to the derivative of the entropy with respect to the energy.
Yeah.
So, well, that in a sense defines a conjugate variable, but in a very weird sense. Okay. In a very weird sense. So what you're trying to ask me is how could I make a description in which the energy is fixed? I have to think about it. I'll try to give you an answer if I manage to do it while preparing all the lectures, okay? I forgot here to write it down. Yeah. All right, so now let us now write down an important thing, which are the Maxwell relations. Now, Maxwell relations are obtained from a very simple idea, which is the following. If you consider the differential of any one of these guys, written up as for example, for the energy, as dE equal to TdS minus PdV plus mu dN. This is of course written up under the assumption of a reversible infinitesimal process, and it's an exact differential, right? Now, if it's an exact differential, that means that all the cross derivatives, okay, have to be equal to each other. Otherwise, it could not be an exact differential. What do I mean by this? I mean that, for example, T is equal to dEds, fixing blah blah blah, and but I know that dE dV the second derivative taken first with respect to S and then with respect to V should be equal to the second derivative taken with respect to first V and then S, because this is an exact differential, right? And these cross derivatives have to be equal to each other. Now, what does this mean? This means that if I take, let's read it. This is just the derivative of the temperature with respect to the volume, right? Because the derivative with respect to entropy is equal to the temperature. And then I take a derivative with respect to the volume. And this has to be equal to the derivative of the energy with respect to the volume, which is minus the pressure, right? And then the derivative with respect to the S of that, which is minus the derivative of the pressure with respect to the entropy. Minus dP ds. Okay? And so on and so far. If you now do this for other two variables, you will discover that dt dn is equal to d mu ds, or minus dp dn is equal to d mu dv. Now, notice something very, very simple. It's very easy to remember these kind of things, okay? You just have to remember who is conjugated with whom, right? I mean, so, for example, here, pressure is conjugated with volume. Temperature is conjugated with entropy. You see, one stays on top, the other stays at the bottom. Temperature is conjugated to entropy, mu is conjugated to number of particles, and so on and so forth. There is even a diagram that is written up in the book by Wang. There is a diagram with all kinds of crosses to remember all these Maxwell relations. But essentially, if you want to derive Maxwell relations up to the minus signs, which might be tricky to derive, the other thing you have to remember is, what are the variables I want to use as free variables? The variables that I want to use as free variables will always stay on the bottom, right? For example, if I want to use volume and temperature, so I will have volume, temperature. Then what is conjugated to temperature? Entropy. What is conjugated to volume? Pressure. ds dv equal dp dt. And then I have to think about the minus sign. Okay? It's very, very simple. So I'll let you suffer through the derivation of all possible Maxwell relations at home. Please do it. It's boring. It's super boring. But since you will have to go through all the thermodynamic potentials one by one, you could easily, as an exercise, otherwise it becomes extremely boring, just to read my notes, as an exercise to understand this stuff better, for each thermodynamic potential, write down the Maxwell relations. Okay? It's not that complicated. Now, final thing. So I canceled one thing, but you see, this is the advantage of not having a blackboard. It's great, you know. In a blackboard you have irreversible thermodynamics, and here you have reversible thermodynamics. It's not entirely true because it's not reversible. All the dissipation happens in the system itself. Anyway, okay, so let me give you an example of how to use, for example, all these Maxwell relations for something useful. Let us consider the free adiabatic expansion of an ideal gas. So we have an ideal gas which is constrained in a certain volume. Let's call it V initial. And then at some time t, we just open the container and let it expand in the volume V final, which is larger. Okay? So this is an experiment that was done, for example, by Kelvin, I think. And is the experiment in which he measured that the temperature of the ideal gas was not changing, right? So now, how do we do how do we compute the entropy? Well, for example, since the internal energy is not changing in a free expansion, right, because it does not depend on the volume, we could compute it by taking an isotherm that is connecting these 2 points with an initial volume and a final volume reversibly. Okay? So we just compute delta S as integral V initial V final ds along an isotherm. So if you want integral V initial V final dV ds dV at constant temperature. Okay, so now we have an isotherm. So we are fixing temperature. And then we are using as other variables volume and number of particles is, let's say, fixed. Therefore, the candidate to think about this problem is the Helmholtz free energy. Okay? The Helmholtz free energy, which is defined as F equal to E minus T times S, dF is equal to minus S dt minus P dV, and of course we have S equal to minus dF dt and pressure equal to minus dF dV. Now it's obvious now that the Maxwell relation here will tell us that ds dV at constant temperature is equal to dP dt at constant volume, right? This is exactly the cross relation I was looking for. You see it because, well, here I have temperature, entropy, pressure, volume. The cross relation. Right, so now let me plug this in there. I get delta S equal to integral V initial V final dV dP dt constant volume. But now I know what is the pressure, right? Because I know that P times V is equal to N times R times T. Okay? So dP dt at constant volume is going to give us VI V final N times R dV over V. And then I do the integral and I get N times R log of V final over V initial. You see? Very simple calculation. So that's one possible application of all this thing. Let us try to do another one, the last one. Suppose that we have two systems that are in contact with each other. And one system has an energy E1, number of particles N1, and a volume V1. The other one has an energy E2, number of particles N2, and a volume V2. So now, dE is equal to TdS for the total system, right? So the dE is the total energy. So it's E1 plus E2. N is the total number of particles, N1 plus N2. And V is the total volume, V1 plus V2. So dE is equal to this. Why am I using the internal energy? Because I'm fixing number of particles, volume, and, well, it's a thermally isolated system, and therefore the entropy. So now, ds is going to be equal to dE over T plus P over T dV minus mu over T dN You see now, what? It's okay. So now ds dE is equal to 1 over t. ds dV is equal to P over t. And finally ds dN is equal to minus mu over t. Now, if I now consider S as a function of E, N, and V, so you see why I was telling you before that 1 over t is conjugated to, in that weird sense, okay? So if I now take S as a function of these things and I consider ds, I see that this is ds 1 over d1 minus ds2 over d2 d1 plus ds1 over dv1 minus ds2 over dv2 dv1 plus ds1, I will explain this in a second, minus ds2 over dn2 dn1. Now, this is just a total variation of entropy, assuming that I'm fixing E, N, and V, but E1 and E2 can vary, maintaining this constraint. Now, if E1 and E2 can vary, maintaining this constraint, then it's clear that, well, you pick a minus sign here because you're using V2 as a variable, and that's it. And this is how you will get it. And now, what you want is that the system is in equilibrium. Now, if this system is in equilibrium and it's thermally isolated, right? So it's not exchanging any heat with the external environment, then the total change in entropy has to be equal to 0, because it cannot exchange anything with the exterior. So this has to be equal to 0. And therefore, since we have E1, V1, and N1 as free variables, that means that each one of these terms here has to be equal to 0. But then, the fact that each one of these terms has to be equal to 0, for example, tells us that ds1 over E1 has to be equal to ds2 over E2. What does this mean? ds1 over E1 is equal to 1 over T1.
The temperatures have to be equal.
Temperatures have to be equal. This is something obvious that we all know. If I have two systems that are in contact with each other and they are isolated with the exterior, the condition of equilibrium between these two systems is that the temperatures are equal. If the temperatures would not be equal, there would be a flux of energy from one part to the other, and therefore the system would not be in equilibrium anymore. So you will have to have, for equilibrium, you will have to have 1 over T1 equal to 1 over T2, P1 over T1 equal to P2 over T2, and mu1 over T1 equal to mu2 over T2. Now, in these two cases, if you put T1 equal to T2, you see that this is the obvious condition of having equal pressures, otherwise particles will move, or equal chemical potentials, otherwise particles will move, etc., etc., etc. Good, so we're done. So today we have 15 minutes of vacation. So tomorrow we're hopefully going to do some more applications of thermodynamics, calculations of entropy, and various other things. Okay?